Hi, guys. So, you would have heard about quantum teleportation. What happens is that you have a particular state, and using entanglement, it gets teleported to a distant location. So, teleportation has been done on the small scale with, I think, the largest system to date is 2 qubits, but never really on larger systems. And so, in order to reach larger systems, we really need some kind of ideas which we've been working on in this group for some time. So what we're going to talk about today is related to this point. It's actually about remote state preparation, which is almost the same thing as teleportation, except that instead of teleporting an unknown state, you teleport a known state instead. So we've got Manish. He's been working very hard on this remote state preparation, and so he's going to talk about that today.
Also, watch out for the Urdu language part of this talk.
So, hi, Manish.
Hi, everybody. Good to see you on the other side. So, in today's discussion, I would be going to discuss about the remote state preparation of a quantum state, and mainly I will be talking about for macroscopic system. Here, I will going to start with the main protocol, how we can achieve the quantum state preparation from one location to another location. This is for single qubit. As we know that any single qubit can be described by a general form, which can also be visualized on the block sphere. 0 and 1, they are the levels. They are the basis for this Hilbert space, and any qubit can be expressed in terms of this basis. Theta and phi are the corresponding block sphere angles, as we know. Now we need to transfer this information to other side. So how a remote state preparation protocol prepares the desired state at the another location. For this, they start with two parties, let us say Alice and Bob, and Alice wants to transfer the information of this unknown qubit to other place. They, for achieving this, they start with the entangled state, as I mentioned earlier, and Alice measure in suitable basis so that the state of the entanglement bit of the bob also collapses after such measurement. What basis she can choose? Since 0 and 1, they are the standard basis, we can always perform a transformation so that this basis, we can go to qubit basis. This two states also form another basis for the Hilbert space. And after such measurement on her part of the entanglement bit, the bob state also collapses into the desired basis. Here we choose the singlet state. The good property about the singlet state is that they are rotationally invariant, and in whatever basis I want to work, the structure of the singlet state looks the same. Here I write in, here we see in terms of the 0 and 1 basis, and which is the standard basis or Z basis. And in terms of the unknown qubit basis, the structure is same. 0 and 1, they are complement to each other. Similarly, theta phi and theta phi bar, they are complement to each other. They are orthogonal to each other. And we can see that there is some information that after performing such measurement, the state on the bob side seems to be prepared. If we look into the details of what type of state is being prepared, we can see that for one of the outcome, the desired state is prepared on bob side, which is nothing but arbitrary state which we want to initially prepare. For the other half of the outcomes, the state is arbitrary, but it is not same as the desired state. We can more visualize if we calculate the Pauli spin averages, and we see that there is a flipping of the spins, flipping of the qubit state for this state. Now, next question is that can we do some classical communication or classical corrections by some communication so that we can correct this state. So if we apply Z and X gates to this state, then we it seems that the state looks like same, but still there is a phase ambiguity. And we can see that because these theta phi and theta phi bar are complement to each other, there is no unitary operation which can change the another state to the usual. So that is, we can say, is the limitation of remote state preparation, or or limitation of the basis selection, I would say. In order to rectify this, or in order to achieving the same, we generally use the equatorial state, for which there is no such ambiguity, because theta doesn't matter here, and phi we can, and this phase we can simply correct it by applying the z operator. So all the equatorial state, they are transmitted with the same state. So that achieves the whole process, which is slightly simple compared to teleportation, as we see that in teleportation, the qubit is not known.
Yeah, so this is why normally people only look at the equatorial states, right? So when you normally talk about remote state preparation, then it's always on the equator, and it's basically for this reason. You could do something more general, as you showed, but then basically there's just no way to completely classically correct it, because there's always one minus sign on one of the x, y, or z variables, and you just cannot get rid of it. Yeah.
So now, same question apply if we have multiple qubits. We have a collection of n such single qubits, and information is stored in all such qubits. How we can transfer the information? We use the Bose-Einstein condensates, for which we see that all the atoms, they condense in the single energy level, for which I can describe the whole state of the system by a single macroscopic wave function. And the states, the characteristic of the states for such system is that they are more robust against noise or particle losses, because if I see the structure, then there are multiple copies of a qubit, and even if some particles are lost, then still the information is stored in other particles. So in our work, now I will briefly mention about our work, what we have done for such type of system to achieve the same, to transfer the state. So again, the state which we transfer on the other side looks like this way, which can be visualized on block sphere. This u theta phi is the appropriate unitary operation, that is generally rotation, by which we can orient in along any direction on the block sphere. And this k are the Fock states, which generally tells the number of the particles in the two-component system. Again, we use the entanglement property, and the entangled state for such system, for such n collection of particles, will be same. If we just make an analogy with the qubit state, they are correlated, and I just write here in the arbitrary basis, so that it could be visualized on x, c, or y basis. In order to transmit the information, again, Alice will perform suitable measurement on her part of the qubit, so that the desired state on both sides will prepare. And last process is just to tell Bob that whether he receives the desired state or not. For half of the projection outcomes, the aim is achieved with probability for each event to be 1 by n plus 1, which I think can see for qubit case is half.
The probability there, Manish, is so that you just mean the probability of each outcome, actually, right? So actually the success probability is 1, right? Because for every case, you can just do the same type of correction step as for the qubits, right? That probability is just the measurement probability, and it's not a success probability, right?
This is the measurement probability of each outcome. that transfer some state on the website,
So
not the success. So yeah, now I would like to just describe more on the success of the protocol. So here we first see the spin averages of the desired state, which is being transferred to Bob site. So they are calculated in the usual way. So the dashed lines here are for ideal cases when what we expect from the ideal remote state preparation protocol that we have studied seen. Since this entangled state for n qubit system we cannot prepare because this is the spin APR state which we call. So rather we use the squeeze states. So that one approximation we have used here. So that's why there is a slight deviation, but from the ideal cases, if I see the different projection outcomes, since there are n plus 1 projection outcomes, so I have shown here for 4 such projection how the properties of the transfer state looks like. So for the extreme projection for which spins are aligned in same direction, then uh, the the transfer state generally is in agreement with the ideal ones, and the desired state is prepared. However, any small deviation we can rectify if we generally take large atoms. We can also understand the characteristic of the state that is being prepared, whether it is quantum state or or uh, or classical one, by looking at the Wigner functions. So here I've plot the 3-dimension Wigner plots. From the protocol, if we match the Wigner function to the corresponding ideal ones, then we can see that the nature of the state that is prepared is also in agreement with the ideal ones. And finally, we can also see the error of the protocol. If the transfer state on the block sphere is at the same location for the ideal case that initially we desire to. So this is calculated by the distance formula. If I have 2 states on the block sphere, by calculating the deviation between the 2 states, then I can get an estimate for the error. Overall, the states which are being prepared, they are of the right nature, right state that initially we intend to. We can also post-select those outcomes which is giving more errors. As we earlier seen that there are some outcomes for which the state is not is desired state. So we can just remove or post-select those outcomes so that their contribution doesn't account in calculating the overall error. And we see that if we plot with the particle number, the average error, then the error will goes down. So this presentation is based on our research article, which is published, and more information we can find it here.
Okay, thank you, Manish. Do we have any questions?
What would happen if there is some like atom loss during the transfer process?
No, I would say it would only decrease the amplitude of the signal which we are obtaining in our measurements. Otherwise, yeah, because some qubits are lost, so overall signal to error ratio is going to get smaller.
But the state you transfer would not be perturbed, right? It would be still the kind of the same state, but
Yeah, if I see by experimental, there is always fluctuation in the atom number. I mean, it is not always fixed that we can always fix the atom numbers for BEC. There is always thermal fluctuation. Some atoms are lost or added or subtracted from the system. That analysis also been done, and I think I have not included here, but we see that the overall spin averages, they are same.
Yeah, so it this kind of thing is very sensitive to like what kind of state you have. So if you have like a cat state, then it's very sensitive on the loss, right?
Okay.
Whereas if you have a squeeze state, it's less sensitive. under loss. And so this type of state example of a squeeze state. So it's not quite as sensitive as cat states, but of course, if you have any loss, it will always reduce the coherence in the system, and then the entanglement would drop, and the usual kind of story.
You said something like quantum information is being transferred. So I want to understand what you mean by quantum information, because here I think you are transferring theta and phi, which I think are classical information. So, but you said something that quantum information is being transferred. So could you really clarify what you mean?
Quantum information is the superposition, right? It is 0 and 1 are classical results for sure, but all the information is in superposition. That's a good advantage of qubit. We can store infinite amount of informations by superpositions of the classicals. So that superposition is unique to quantum.
So in all this, okay, so if you're saying, okay, so why, if it's classical information, right, it's totally characterized by theta and phi, right, then what I could do is just simply ring up Bob, right, and then tell him theta and phi, yes? And then you say, well, that would do the job. So, why did you do all that, right? And that's perfectly true in this case because Alice knows theta and phi, yeah? But actually, here, what they actually do is only send one bit of information, of classical information in the end. Manish didn't say it so much here.
So is it like super dense coding?
You might say super dense sort of transfer of information. Yeah.
Okay.
So you actually achieve sending theta and phi in principle, infinite precision if everything was perfect, with only sending one bit of information. It's a quantum state at the end, so I think that's all he means by that. But maybe this is what makes it a little bit more different to just sending the classical information.
I also have a question. Can you say something more about post-selection? I didn't really get how post-selection works in this protocol.
Yeah, that is okay. Good question. So I think if I see the formula, then I have weighted the error function with the probabilities. So this probability will determine, and this probabilities for the high error cases is quite low. So that if I go here and if I see that on the error port for transmitting different information over the different block sphere, then generally almost all part of the block sphere the error is low. But there is some region which is actually close to south pole, then error is quite high. But if I do the analysis of probabilities, corresponding probabilities, then the corresponding probabilities are quite low. So in averaging those, in average error calculation, if I properly weight with the probability with which these outcomes occur in the protocol and multiply with the, just take the corresponding error, then it will take care of that.
Just to give a more direct answer to the question, these extremal k's, k equals 0 or n, perform the best.
Okay.
Yeah. So the closer you are to the edges, somehow it works better.
Okay.
So you always know which ones to first select.
All right.
Yeah.
Thank you.
So let me just ask this. So the whole goal of this is to transfer some known information from, say, Alice to Bob. So can we really use this, in the traditional sense of something like teleportation?
Yeah, see, I think teleportation, I would say it is a little bit advanced process because here the qubit state is known to Alice. But for teleportation, it is unknown. Then to set up the correlations for both theta and phi, I think I would be needing one more qubit. Like here, we generally deal with two large qubits so that they are entangled.
Yeah, that's right. That's the extra ingredient you need. You need a Bell measurement, and well, we know how to do that now.
Yeah. So
Yeah.
we need a Bell. So Alice can transfer information, known information to Bob, right? But we need the Bell measurement to complete it.
To do teleportation, yeah, we need additional Bell measurement, which we know how to do. So yes, it can be done. We haven't written the paper, but we're keeping it a secret, so we can write another paper.
Not really a question, just a comment. Alice is so beautiful and looks more feministic, and Bob is, I don't know. So is this gender equality or? So
this is me, and this is Alice.
Yeah. Yeah, but this sexism in physics. What exactly are you showing us here? That's what I'm actually getting at.
I think in terms of physics, it is a lot, or we can say in terms of quantum physics, it is a lot.
There's a lot of
maybe
stuff.
physics is a broad term, but it is a quantum physics topic. And in terms of application, or I don't know, I mean, don't you find interesting that if I have to transmit information from one place to another, and it is not the usual information, it is quantum information. So that is, I mean, very involved process. Because there is always not simple, as I mentioned earlier.
But I mean, okay, so I have to confess that actually that's sort of like my figures. Like I use that Alice and that Bob. But it's because one needs to be Alice, one needs to be Bob, right?
I agree.
So Alice in Wonderland, yes. And then Bob, so I had to think of like what are the famous Bobs, right? I couldn't really think of famous Bobs. I couldn't think of famous Bobs.
So many Bobs are getting triggered right now.
Yeah. So, Bob, the minion Bob seemed to be reasonably, well, you want a cartoon and not a human, like a photo of,
Bob
like
Dylan.
Bob Dylan or Bob Saget or somebody like this, right? You want a cartoon, so you're limited. It would be either him or Bob the Builder. I can't think of any other Bobs. But yeah, it's sexist.
Yeah.
Fair enough.
Basically, transmitting any particle.
Yeah.
It is just
But
information.
then what should we
that
do?
is-
Should we make Bob more beautiful or should
I
we
don't
make
know.
Alice less beautiful?
I know it. You have to balance it
Whatever
to
is
be
easier.
equality. Because one looks so, I don't know, and the other one looks,
Just say Bob 1, Bob 2.
No, Bob 1, Bob 2. Then where are the female? So it has to be.
Okay, then Alice 1, Alice 2.
There needs to be A and B.
A and B, right?
And then there will be like A1, A2. There will be notation problem.
I like it is just
Man, this is so confusing.
This is the questions I get. I did all this research and this is what I get. Okay, so thank you very much, Manish, for that. It's very interesting. If you enjoyed this video, then please don't forget to subscribe to our channel, and we will see you next time for other quantum-related topics.
Also, watch out for the Urdu language part of this talk.
Oh yeah, that's right. You're gonna repeat this all in Hindi now, right?
Oh yeah.
And
Yeah.
we are going to ask all our questions also in Hindi.
That would be. Yeah. Can you teach us some?
That's what I wanted to prepare.
We'll become a language learning channel.
anytime.
Can we choose the actors who dub our voices? I mean,
That'd be cool.
just to dub the voices, right?
Oh, just to dub it.
Yeah.
Oh, okay.
Just like in the movies.
Yeah.
Oh.
Yeah. I like that. Yeah. Okay. All right. We're gonna do that. Okay. All right. Okay. Well, thanks for watching.
Bye.
Goodbye. Bye.
Bye.
Bye.